Well, with this one here, you might realize, well, this matches perfectly with the formula. Well, yes, it does match perfectly with the formula. If you did choose to use that formula, you would realize your u corresponds to x. So then you would get an x instead of this u here. Then you go natural log of your 1 plus e to the x plus c. Now, question is, where does that formula really come from? Well, what you could do, instead of having a 1 on top, you could rewrite the top. We could basically add 0. You add an e to the x and subtract an e to the x. Adding 0, you know, doesn't really change your problem. Well, then we could write it as two fractions. The first two over the bottom, and then your second or your third one on top over the bottom. You notice the first one here is pretty easy. That's just a 1. And if you integrate your 1 dx, that's where your x comes from in front here. Now here, it's a negative. You'll notice that the bottom ends up being u. 1 plus e to the x is u. You'll notice your du then ends up being just your e to the x dx on top. So it really integrates into the natural log of the bottom, and that's where that formula comes from. Now this one here doesn't appear to fit any of your basic rules. However, if you do choose u to be what's in the brackets right here, then it works out pretty easy. There is another way to use u, but it works out pretty easy to let this be u. You know your du would be the derivative of your natural log, which you know is 1 over the inside. But then you got to use the chain rule and multiply it by the derivative of the inside, which is your cosine times your dx. Or du then is really just your cotangent. And you'll notice you do have a cotangent showing up here. So this right here is really just your du, where this right here is really just your u. So it's really just your integral of your u du. Well, you know when you integrate a u, you're going to have to increase your power by 1, put a half in front. Then all you have to do is substitute in what u is. It's just your natural log of sine of x, then all squared on top times a half plus your c. Well, this one here, once again, you'll realize, oh, there's a formula for that one. Happens to be formula 63, where your u then would correlate to your 2x. So du would be 2 dx. You'll notice you don't have a 2 showing up, so you're going to have a 1/2 hanging around. And so if you just use your formula, you're going to have your 1/2 there, tangent of your 2x, plus your negative u, which is your x, plus c. Now, where does that formula really come from? Well, you don't have a formula for tangent squared. But you'll realize from your Pythagorean theorem identities that tangent squared is really a secant squared minus 1. Well, then you do your integral of your secant squared, which you should realize is just the tangent. And then you got to integrate your 1. Integrating 1 isn't too bad. And then in this case, once again, your u was your 2x, so you plug in your 2x for your u there. Your 2x here over your 2 is just your x. So even if you didn't have that formula, yes, you could work it out. Not necessarily as straightforward and obvious as it is with just your formula. So here, for the most part, it's a summary of ways to integrate. If you have something squared, just FOIL it out and then integrate. You may need to go ahead and separate it into two fractions. You may need to go ahead and, say, do longhand division like we were doing on this one right here. Now, you notice if you're trying to use a lot of the formulas in the back of the book, they have something squared minus something squared. Well, 1 is something squared, and here we have something squared. Your initial problem wasn't that, so you might actually have to complete the square with this here to get it in the proper form. Or here, we added a special form of 0 so that we could get it to work out nicely. Or you might have to use your Pythagorean theorem identities, or use a special form of 1 with your conjugates on your trigs and then rewrite it. Those are all different ways you may need to try to use in this assignment. And here's just some of your basic integrations that you were looking at in the back of your book.